Hi guys, so today we're going to look at inverses. So again, inverses, similar to operations in composition, is going to be something that we use for all of our functions and not just the root functions we've been looking at. So to find an inverse, this part's pretty important. What you need to do is you're switching the x and the y. Okay, so an inverse is a different operation. It's the opposite operation. Okay, what an inverse is not, an inverse is not a reciprocal. Okay, sometimes people get confused because of that little -1, right? That is not an exponent on the function. It's not saying you move it to the bottom. Okay, that's just the notation that means inverse. Okay, so again, an inverse is not a reciprocal. Okay, an inverse is a different operation. So one place you've already seen inverses was in geometry. Like if you were solving for sine A equals 12 over 13. Okay, you solved that by using an inverse. You had to do A is equal to sine inverse of 12 over 13. Okay, so that's an example of an inverse. It's a different operation. Okay, it's not the reciprocal. So to find the inverse, what we do is we switch x and y. So f of x means the same as y. So this would become x equals 2y plus 4. So just get y by itself. And then instead of just dividing by 2, I'm going to rewrite this in a form you're used to seeing it in for graphing. So both of those things are divided by 2, so I can rewrite this as 1/2 x minus 2. And again, I'm just going to write my final answer with that inverse notation. So f inverse of x is equal to 1/2 x minus 2y, or minus 2, sorry. All right, so let's look at another one. This time there's a specific restriction. It says x is greater than or equal to 0. The reason that we need to do that is so that our inverse is actually going to be a function. Okay, so let's just go ahead and work this one out. So switch x and y. So I get that x is equal to y squared minus 2. So x plus 2 is y squared. So I get that y is plus or minus the square root of x plus 2. Now if you think about it, if you were to graph this, you'd be graphing the positive square root and the negative square root. But that wouldn't be a function because it doesn't pass your vertical line test. So what we have to do is we have to look at our original problem. Our original problem said that x had to be greater than or equal to 0. Well, if we're switching x and y's, then these statements over here are going to be really important for us. So that means the range of the original function is the domain of the inverse. And it works the opposite way. The domain of the original is the range of the inverse, and that's because we're switching x's and y's. Okay, range is y's. They become the x's. Domain is x's. They become the y's. So that means that if the domain was restricted on the original, then the y's have to be restricted on the original. So if the y's are restricted, it's not going to be both the positive and negative square root. In this case, it is only the positive square root because that's when y is greater than or equal to 0. All right, so then to see this a little bit better, I'm going to draw this on a graph. Okay, so to graph this function, this is a square root function to the left 2. I'm going to pick an easy point to plug in, like -1. -1 plus 2 is 1. The square root of 1 is 1. I'll pick another point. Let's pick 2. 2 plus 2 is 4. The square root of 4 is 2. So there's my square root graph. Okay, and again, I just did the positive one. If I did the negative, it'd be those points down there, but it's no longer a function. And then graphing the original, okay, that's a quadratic, that's a parabola, shifted down 2. So if I plug in 1, 1 squared minus 2. If I plug in 2, 2 squared minus 2, actually gives me the same point. And this graph goes this way. Now the way your inverses will look, because we're switching x and y, those graphs are reflections over the line y equals x. That's why they happen to share that same point, because the x and the y are the same point. All right, so let's look at 2 more examples. If you feel pretty comfortable, go ahead and pause the video and try this one. But I'm going to go ahead and work this one out. So I'm doing x is equal to negative y squared. So negative x is equal to y squared. So I'm going to square root both sides. So y is equal to the square root of negative x, and it could be plus or minus. Okay, so to figure out which one it is, the domain of the original means that the range of my inverse is going to be y is less than or equal to 0. Well, the square root of negative x would reflect over the y-axis, okay? But in order for the range to be below 0, I would have to have the negative square root of negative x, because again, that would reflect it down and also to the left, so my range would match. So that's going to be my inverse for this one. All right, let's look at B. So let's switch the x and the y. And this is very similar to the process we just did, solving square root equations. So not minus 2, I'm sorry, divided by 2. And instead of dividing by 2, I'm going to go ahead and write this just as 1/2 times it. Since we're dealing with equations and graphs, I want it to be similar to the form you guys are used to seeing with your transformations. So then I'm going to square both sides, which means I'm squaring everything on the left side. So this is now 1/4x squared. And then I can add 3. So this is my inverse. Now, what we have to consider here, though, we need to be careful. Okay, we've talked about domain a little bit. Now, this function, this is a square root. Okay, the entire parabola in my inverse is not going to be my inverse. Okay, that's not the whole thing. So I have to make sure I restrict the domain in my answer. Okay, just like we said, the domain of the original is the range of the inverse. The range of the original will be the domain of my inverse. So I need to restrict that domain to actually make it the inverse of this function. So I need to find the range of my original. This has not been shifted up or down. It has not been reflected. So the range is going to match the parent function, which is from 0 to infinity. That means the domain on my inverse will also be from 0 to infinity. If you want, you also can list that as x is greater than or equal to 0. All right, so again, domain of the original will be the range on the inverse. Range on the original will be the domain on the inverse. All right, so now we're going to just determine if a function's inverse will be a function. Okay, so we learned to determine if something was a function, we used the vertical line test. So what we're going to use is something called the horizontal line test. So the horizontal line test will tell us if a function is 1-to-1. 1-to-1 means that every y has one x. So that means that it's going to pass the horizontal line test. It also means if a function is 1-to-1, then the inverse will be a function. So the absolute value of x minus 3, that would be an absolute value graph shifted to the right 3. So the general shape would look like this. This graph fails the horizontal line test. So that means that the inverse of this would not be a function. We would have to restrict the domain. It also means that function is not 1-to-1. Right? Cube root, that was shifted right 4 and stretched. Okay, it's going to look something like this. Okay, that general shape. We'll shift it to the right 4 though. It's kind of a bad picture. So something like that. All right, even though wherever it is though, your cube root functions will pass the horizontal line test. There are no y's that are repeated. So the inverse of this will be a function. It actually is going to have a similar shape to your cubic graph. And then finally C, that is a parabola that's been shifted right 4 and down 3. And that also fails the horizontal line test, which we've talked about. In order for your inverse to be a function, then you have to restrict the domain. So something else that we can use inverses for that are helpful is we can use inverses, or we can use determine if functions are inverses by using composition, which we did last class. So what we're going to do is we're going to do composition with f of g of x, and then we're also going to do g of f of x. Now, if this works out, we will get x, just x by itself, for both of our answers. So let's start with f of g of x. I'm going to make this a different color so it's easier to see. Okay, so if I do f of g of x, the g of x function replaces every x in the f of x function. So this becomes 3 1/3 x plus 1/3, and then the original function still has a minus 1. So this becomes x plus 1 minus 1, which is just x, which is what we should get if they are inverses. But we have to do this both ways. So we also have to do g of f of x. So g of f of x means the f of x function replaces the x. So I'm going to do 1/3, replace the x with 3x minus 1. And then my original function had plus 1/3. 1/3 times 3x. And I'm left with just x. So I get x for both of them. So yes, those functions are inverses of each other. All right, looking at b, again, very similar. I'm going to do f of g of x. And if you feel pretty comfortable, I'd pause the video and try this one on your own. So this is going to be the 5th root of 5x to the 5th minus 9. That replaces the x. Okay, the original still has plus 9 in it, and it's all divided by 5. So simplify the top. This is the 5th root of 5x to the 5th over 5. That gives me the 5th root of x to the 5th, which is x. So far so good, but we got to check both of them. All right, so let's do g of f of x. All right, so I'm going to replace the x in this function with that big cube root or 5th root. Okay, and that is raised to the 5th power. Well, a 5th root to a 5th power, that root's going to go away. Okay, 5 times something over 5, those 5's cancel out. So I'm left with x plus 9 minus 9, which is x. I get x on both sides. So yes, these are inverses. Now, it won't always work out that way, but in these two examples, it did. Okay, so again, do composition both ways, f of g of x and g of f of x. And if they both end up as x, then those functions are inverses. So the last thing we're going to look at is just tables and graphs, okay, doing the same thing, okay? Just by looking at the table, we can tell if these functions are inverses. Okay, if they are, the x and y's should be flipped, and they are. My x became my y, my x became the y, x became y, and x became y for every single one of those. So on A, that is an example of a table that does represent an inverse. On B, though, if it was an inverse, my new table would be 8, 2, 6, 3, 4, 4, 2, 5, and 0, 6. That is not happening. Instead, it's just making the numbers negative. So that is not an inverse. And then finally on a graph, same thing. We're just flipping x's and y's. So this first point on my graph is 0, 5. Second point on my graph is 1, 4. Okay, and let me get one more point on my graph. Let's do this one right here, which is 4, 3. Well, then my new graph, switch x and y, 5, 0. Instead of 1, 4, I'm at 4, 1. And instead of 4, 3, I'm at 3, 4. So there's my inverse function. And again, they look like reflections over the line y equals x. Okay, so that's it for inverses. Again, the biggest thing about inverse, you switch the x and the y. The domain of the original is the range of the inverse, and this opposite way around. The range of the original is the domain on the inverse.